Hello and welcome to the STEMCstudio channel. In this video, we are going to take a look at the geometric product for our geometric number. It's super exciting that we've gotten to this point, and this is where the use of our geometric number, it's really going to become possible to do very interesting things with it. Reflections, rotations, manipulations that you could just never do with ordinary vector algebra. Okay, let's just get started. Let's go. So I'm going to pose a question here. Can we construct the scalar product and wedge product of vectors in a way that makes manipulating them easier and more consistent? Okay, so we're going to drop the arrows above vectors from now on. Okay, they just kind of become too onerous to be drawing vectors over our arrows. And you should just note that if you see these Roman characters A and B, generally that means that you've got vectors. If you see things like alphas and betas and gammas and things like that, mu's, generally we'll keep those for scalars. So it'll be pretty easy if it hasn't been called out explicitly, those will be scalars. And things like bivectors will tend to use an uppercase character, like a capital A or a capital B. And then you'll know that you're probably dealing with a bivector in that situation, if it hasn't been made clear up front. Of course, there should always be a statement up front that says something like this: let A and B be vectors. Okay. All right, so let's get on with this. Observe that A dot B is symmetric. That is, if you change A for B, then there is no change in the sign, and what you get is exactly the same as what you had before. That follows from the fact that A dot B is all about the projection of one vector onto the other and then multiplied by the magnitude of the other. Similarly, or perhaps in a sort of contrary way, a wedge B, which represents the directed area which is spanned by first going along A, then going along B. Okay, recall that. That's our bivector. This is antisymmetric. Okay, if we go along B first, we go B wedge A, go along B first, then A. There's a sign change because this quantity represents a directed area, and if you go around the perimeter, if you do one vector before the other, then there's a sign change. So this is kind of like a key kind of observation that is going to give us a sort of a clue to how we can represent these products in a sort of more efficient, well, I would say a more useful way. Okay, the power of the geometric product is going to come out in a little bit. Okay, so the first thing, let's just kind of like imagine that we try to represent A dot B somehow in terms of some product that commuted, like addition. Okay, A plus B. A plus B is just B plus A. There is no way that we can kind of get symmetry and anti-symmetry out of that. We need to use something that is more like multiplication. Okay, so this is how we do it. We start off by saying, let's just suppose that we can multiply two vectors together. Okay, so here's AB, and I'm just going to split that. I'm going to put a half here, and I'm going to say that's AB plus AB. Okay. Next thing I'm going to do is the old mathematical trick of adding nothing. So I'm going to add a BA, but to keep everything the same, I'm going to subtract off a BA over here too. Okay. And then I'm just going to sort of group these things. I'm going to put my parentheses here, and I'm going to take the half and put a parentheses around here. And I've got two quantities. So AB is now equal to these two quantities, 1/2 AB plus BA and 1/2 AB minus BA. Okay, nothing, done nothing here other than assuming, yeah, let's say that we can do multiplication of vectors. But notice that AB plus BA is symmetric. In other words, if I change A and B over, interchange them, there's no change in the value of this quantity. That's just like A dot B. And notice here that AB minus BA is antisymmetric. In other words, if I interchange A and B, I get the minus of what I had before. That's just like A wedge B. So that suggests, these two things suggest that what we could do in a sort of a definition way is we could identify this quantity with a dot b and a half ab minus ba with this quantity a wedge b. Okay, and then we could say let's just define ab to be a dot b, this thing, and a wedge b. Okay, so let's do that. So here's our definition of what we call the geometric product. A times b is defined to be a dot b plus a wedge b, where a and b are vectors. Okay, and then here's the kind of the conclusion that we had before. We need to add a couple of things to our definitions that will enable us to deal with the multiplication of a vector with a bivector, because so far we've only done a vector with a vector. And the first definition that really gets to solving that problem is this associative definition. So we're going to say that if you multiply AB together first, and then you multiply it by the vector C, then you get the same answer as if you were to multiply B and C together first, and then multiply by A. So this is just associate. You know, how do we associate when we have these products? And because where we put the parentheses doesn't matter, we can just say that it doesn't matter. So let's just write this as you could write this as ABC. That's exactly the same thing. So this is the associative definition, and that definition is going to come in handy for us very soon. Then the final thing is we just need the usual distributive definitions where we relate the geometric product. How does it relate to addition? How does it distribute? And then we have the very usual distribution laws for the left and the right-hand sides. I'm not quite sure which one you define as the left and the right in here. I can't remember. But it doesn't really matter. Okay, so let's just look at a few kind of little conclusions. Let's take E1 times E2. Okay, now remember E1 and E2 are our basis vectors, and that basis is assumed to be orthogonal. So E1 dot E2 is 0. And in addition, we assume that we're in Euclidean space, so E1 dot E1 is 1. Okay, so actually you could summarize that by saying that we have an orthonormal basis, which is basically saying it's orthogonal and it's normalized in the sort of the Euclidean sense. Okay, so we've got now this conclusion: E1 times E2 is E1 wedge E2, because E1 dot E2 is 0. Okay, so that's kind of useful because we've talked a lot before about E1 wedge E2, but now whenever we see E1 wedge E2, we can kind of collapse it down into the E1 E2, and that becomes really handy because it's very easy to multiply this by another vector using the associative law. Okay. The next thing we might conclude, for example, is that E1 times E1 is 1, because E1 is just E1 dot E1 plus E1 wedge E1. And of course, E1 wedge E1 is 0, so E1 is just E1 dot E1, and that's 1, okay, because it's Euclidean. And then here's an example of the application of the associative law. E1 times E1 E2, this is initially multiplied together first. We can use the associative law and we can just sort of regroup these and say, let's multiply E1 by E1 first and then by E2. Well, E1 times E1 is just 1, and 1 times E2 is just E2. So you can see that the introduction of the geometric product has made the manipulation of these expressions, this algebra, a lot easier. Okay, and it's going to go further than that, because the geometric product is going to enable us to divide by a vector very soon. Okay, so let's kind of like tabulate this as we did before for other products, so that we can implement the whole thing in our geometric class. Here's our geometric class over here, right? Okay, so we just summarize on this in this column the different parts of our geometric multivector. And we've got the right-hand side over here, the different parts of that. And then here are the products. So a scalar times a scalar, LARA. And you can see this whole row here is just really this scalar value multiplied by the thing that is on the right-hand side. So you can see RxE1 there, multiplied by LA. Okay, so pretty simple there. This column 2 as well is just this scalar value multiplied by this. So these columns are rows and columns are pretty easy to justify. The calculations in here we should just verify, and I'm going to walk through these, and then I will leave you as a sort of an exercise to verify the exterior product. Okay. So let's just kind of like convince ourselves that these are correct. LXE1 times RxE1, that's just LXRx with E1 times E1. E1 times E1 is 1, so it's LXRx. Here we got LXRY, E1 times E2. Well, E1 times E2 is just E1 wedge E2, so LXRY, E1 wedge E2. And E1 wedge E2, recall, is our kind of like basis bivector. Okay. About this guy, we've got LXE1 times RB E1 wedge E2. Well, we can rewrite this one as RB E1 E2, and now that makes the multiplication much easier because it's just LX RB, we just pull the scalars out, and then it's E1 times E1 E2. Well, E1 times E1 E2 is just this here, so it's E2. So we just left it on E2. Okay, pretty easy there. What about this guy? Ly E2 times RxE1. Well, it's Ly Rx, that's the scalar part, and then it's E2 times E1. Well, we don't know E2 times E1 directly, but it should be obvious from this that if we flip the right-hand side, there's a sign change. So the left-hand side, when we flip it, is also going to have a sign change. So E2 E1 is just minus E1 E2, and so that's minus E1 E2, and there's the little minus sign in there. So don't lose track of that little minus sign there when we do our computation. Okay, what about this one? We've got Ly E2 times Ry E2. That's very easy. Ly Ry, and then it's just E2 E2, which is E2 dot E2, which is 1. Okay. Ly E2 times RB and this thing again. We'll bring the scalars out again. So we got Ly RB, and now we've got E2 times E1 wedge E2. And then we need to do a combination of converting the E1 wedge E2 to an E1 E2. We need to flip over the E2 and the E1, so it's minus E2 E1, so that we can multiply it by this left-hand side and have the E2s cancel. So if you work that through, just check that, you'll find that you've got a minus sign, Ly RB, and then we're going to be left with the E1 because the two E2s are going to, in a sense, cancel because they'll be E2 times E2, which is just 1. Okay, pretty straightforward, really. Nothing but kind of high school algebra to prove all these things, and just kind of like methodically going through the steps. In fact, I'm not even going to go through the last line here. Okay, so this is our multiplication table, and now we can very straightforwardly implement it in our multivectors in our geometric multivector class as we have before. Just look at this table just to kind of pick out the values more easily. You'll see this main diagonal column contains everything that becomes the scalar value. So that's what we need to look for when we're constructing our scalar value. You'll see that the opposite diagonal contains all of the bivector values. So this is how we're going to build the bivector component. And then to look for the E1, E2s, you can actually kind of do it like this way. So see, here's E1. If you go diagonally down to the left, you've got that. Now, of course, if I kept on going diagonally down to the left, I'd go off the diagram. But what I can do is, if I imagine this wraps around, I can kind of like come in here, there's the E1, and come down here, and there's the E1. Just kind of like interesting patterns actually occur in this. So here's the E2. Looking for all the E2 components, I go down to here, then I go off the table. So I come in here, there's the E2, and there's the other E2. So that's going to enable us to just read off these things very quickly and put them in our geometric class. Let's go and do that. All right, so I'm going to keep this somewhere handy. I'm going to bring our Explorer back, and I think I'm going to set things up here so that I can at least look at our printed output. The diagram we're not really using yet. So here are our multivectors A and B, and let's just print those. As A and B, and you know the big question is, what is A times B? So let's answer that by saying A times B is A times B. Okay, and yeah, we're not really getting anything sensible back yet, but we know that's because we really haven't defined the operator yet for multiplication. Now you'll know that if you've been following this, that I'm doing something where I first define a method that is the same thing as the multiplication, and then I implement the operator overload in terms of that method. Okay, that's an approach I'm taking because I think it'll be useful later on when we consider how we can make excuse me, very efficient multivectors for computational tasks in the browser. So I won't go too much into why we're doing it, but let's just say we're going to take that approach. Okay, so we need a method called mul in our E2GA. So let's put that guy in sort of here. Here's mul by scalar, so we'll just put mul in here. It's going to look a lot like this left contraction in terms of the fact that I think it's going to be useful again to pick out the various parts like this and then just to write them down and put them in. So what we really have to do is modify this section over here. Okay, so let's grab that, copy it, and put in mul. Okay, and now we just need to read off our table, so probably be convenient just not to run the code for right now. And here's our code. Let's get rid of the Explorer. I'm just making this super convenient. I have to work within the limitations of the screen capture space. Okay, so let's read off the scalar part. We have I want to actually leave that exterior product off just so that we accidentally don't try to use it. We've got LA-RA, that's what we've got over here. LX-RX, we've got that over there. LY-RY, we've got that over there. And LY and LY, sorry, go down diagonally, minus LB-RB. It's very kind of easy to make little mistakes like that when you're transcribing these things. However, we will actually fix that because we're going to do some serious testing on this in a second. Okay, so this is already correct. Actually, it's already got exactly what we need, which does actually hint at something that you should look for in future, and that is that you can almost regard multiplication as being the sort of the definitive, you know, it's got all of the answers. And then when you look at other things like the left contraction, the right contraction, the exterior product, and the scalar product, you'll find that these other products are really just like the full multiplication, but various parts of them have been zeroed out. So that's you know, that's kind of like, it can be useful from a mathematical perspective to know that it can be a way of actually calculating things. Of course, you wouldn't want to just multiply and then use that to implement LCO, because you'd be probably doing a lot more multiplications than you have to do. All right, so let's carry on. What is x? So for x, we need to find the E1 part. There we go, LARX. And we go diagonally down here to the left. We've got LXRA. Well, we don't have that one yet, so we're going to add LX times RA. LXRA, and then we're going to carry on going diagonally, but we come off the table, so we're going to go here. There's the E1 minus LYRB. Yeah, that's exactly what we have here before. Okay, so that's kind of like a good sign that we've gotten it right. And then we come down here and we've got LBRY. Okay, that one's missing, so I'm going to add LB, oops, sorry about that, LB times RY. Okay, so there's X done. All right, what about Y? So we need looking for the E2. So we're going to start off with an LARY, and then we're going to go down this way. So we've got LARY, good. And then we're looking for an LXRB. We've got that. Okay, then we want the next one, which we're off the diagram, so we're going to come in here. LYRA. So we need to add plus LY times RA. It's good. And then there's a minus LBRX, minus LB times RX. Okay, so that's all done for Y. Finally, we've got the E1, E2 component. That's made up of this diagonal here. So let's read that off. We got LARB, already got that. LXRY plus LX times RY minus LYRX minus LY times RX, and then plus LBRA. Okay, so there we have it. We've actually implemented the geometric product. And notice that this involves, 16 multiplications. For every one call to multiply a geometric number, you get 16 possible multiplications. That should give you an idea of how powerful, how much structure is in this geometric number. And generally, as our numbers increase in their structure, they tend to be more expressive in the things that they can kind of like in what you can write down in terms of mathematics and compute. Okay. Something else that you can kind of like sort of observe about this is that there is a certain symmetry in some of these sign patterns, and you can kind of like see here that you get these are all B's, but this is like one of each. You can just kind of like desk check your way through here. It's like, it makes sense if you think about it, that for every one of these you should get a different one, a different value for the component here. So you've got A, X, Y, B, and here you've got A, X, Y, B, A, X, Y, B. I mean, it's just kind of like a useful kind of like desk checking, sanity check, really, that you might have got it right. Okay, let's play with this for a little bit, just to kind of like, we'll just check a couple of simple examples, and then we'll actually kind of like get on to some much more robust testing. So I am going to run the code. Okay, and now you can see already that if A is 2E1 and B is 3E1, then A times B, okay, is equal to 6, because the E1 times E1 has vanished. Okay, let's bring back our index.ts and let's just try something else. Let's try, for example, having a 3 in this column. I'll just get rid of the documentation for right now. So what we've done here is we've done we've done A is, that's interesting. It looks like something is not quite working. We'll debug that. This is kind of like, what will happen to you, and it's happened to me. So we've got a 2e1 here, and we've got 3e2 there, and we're getting a 0 for our multivector. Okay, so did I do something wrong in, say, my table? So when the left-hand side is an e1, stop the code. When the left-hand side is an e1 and the right-hand side is an e2, I should have an lxry. Okay, so here's multiplication, and we're looking at the... that doesn't look right. Look at that. LA, 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 LX, LX, LY. Okay, well, we discovered this in some very informal manual testing. And we probably would have discovered this problem when we implement a much more formal automated testing, which is something we're going to do. Okay, so am I going to correct it now, or am I going to wait till I test? I'm going to correct it now. Okay, let's just correct this. We'll go through again. See, okay, I'm going to check. These are all LYs. These are all LBs. I think that's going to be better. Okay, let's stop it. Let's run and see if we got the right answer. And now we did. Great. So 2e1 times 3e2. Okay, so bugs can happen to anybody, and that's really, it's really kind of like important that works. Before we go fully into the automated testing right now, let's get our operator overloading working. So, recall basically we've done a dot mul b, but what we really want to write is a times b, like that. Okay, and now you can see we've got nothing again, 0 again, and that's because a times b is just not doing anything. So we go back to our class, and what we look for is the done the mul. Now, if you just jumped into here and you're wondering why is it done the mul, there is an article about that. You can go to STEMCstudio here, go to the user guide, go to the operator overloading, and then you can say, okay, the way that we do multiplication is we're using _mul. All right, so you can read about it there, but if you've been following the series, you'll know what we're doing here. Okay, so let's take a look at our done the mul, because clearly we have it, but it's not working. And the reason for that is if you look at the code that's already here, this code is what we implemented when we did scalar multiplication a long time ago, or sadly a long time ago, several episodes ago. And so this is a very simple situation of multiplying a scalar times something, and you can see, in fact, it's very incomplete. I mean, we're not handling many cases here, but actually what we should find is that all of these should be part of our multiplication table. Even scalar multiplication is part of our multiplication table, right? So I'll just illustrate that. So we've got a scalar part. We should have, the left-hand side being a, the right-hand side being a, that's that one. Scalar multiplication, LA-RX, that's the second one here, that's this one. In fact, all we're doing is we're going across this column here, right? We've got a scalar on the left, and we're multiplying it, and we're just basically doing those. But we didn't even implement this one. Okay, so what we're going to do is we're going to say, well, it's pretty clear that our full geometric product that we've implemented now has the scalar product as a sub. I suppose it's a sub. It might be a sub out. It's not really a sub algebra. It's a subset anyway of our full multiplication. So what we can do here is we can just use our method now. So we can return this dot multiplied by the right hand side. Okay. And the warning now is just about unreachable code. So because we're returning here, everything below it can't be executed. So we're getting warnings for that. Just let that go. let's format the document just in case we need to. So let's just kind of like check this. If we're multiplying, and before, if the right-hand side was a geometric or a number, we can handle both cases. And when it's a geometric, we perform the mul. When the right-hand side is a number, we multiply a scalar. And so we should just check that multiplying by a scalar on the right-hand side, so that means we're implementing this column, we should just check that we kind of actually did that completely. So I right-click there, multiply by scalar, and it looks to me like this is not complete because of the 0 here and the 0 there. And in fact, to complete this, we should just really have here this dot A times alpha, and at the end here we should just have this dot B times alpha. Okay, and that truly is multiplication by a scalar. Every component of our geometric is getting multiplied by alpha. Okay, which is, and it's totally consistent with this column in our geometric product table. So I think we're good now. We're going to run that. Just take a look. Yeah, A times B, and we know we're actually using the geometric product now, or rather the operator overloading version now, and we get 6E1 wedge E2, which is rather nice. Okay, so this is great. We've implemented it, but now what we'd like to do is, we're at this point with this class is like, we just want to kind of like check it's correct, and then we can really kind of like use it in applications. And so to check it's correct, we want to really get into a process of automated testing. Now, if you haven't seen the video in the core STEMCstudio program, you should go there now and understand how to add testing to an existing program, an existing project in STEMCstudio. And that would account for why we have these extra files now. You might have noticed that these extra files in the Explorer, the test.html, and those. So I'm going to assume that you've actually seen that video. If you haven't, just pause this video, go and look at that video, and then you will know how to implement automated testing. Okay. So I'm assuming you now know how to do automated testing, and I'm going to click on our tests and run them. Okay, and we've got some tests executing. We got one test, no failures, and these tests are here. So this first test is just a test purely that our geometric number is preserving the coefficients when it's constructed. Okay, so we're really just testing the constructor, that when it's called, it's preserving the coefficients. Okay, what I want to demonstrate here is we want to do a full test of our geometric product, and we want to make sure that absolutely every combination of left-hand side and right-hand side is producing the right outcome. So let's get into that. I think to do this, and the reason why I'm going to focus on the geometric product first before doing the other ones is that it's kind of like the superset product, right? It contains all of the multiplication. So once we get this right, we can kind of like perhaps even use it as a guide just to kind of like desk check our other ones if we have problems with them later. Okay, but what we do want to do though is we do want to make sure that this one works, and then test all of the other ones. Okay, so I'm going to create a new specification for the multiplication, and I'm actually going to test the multiplication method first as opposed to the operator overload, the dundermull, because the first thing is if we run the geometric class without operator overloading, these functions should still work. And the second is that the dundermull is really, because it's using this mull, we can really just test it in a sort of a lot more lightweight way that just checks, the conditions in there. So I'm going to use this as, this is the fundamental thing. So we're obviously using kind of a knowledge here that we actually know how the geometric is implemented. I'm not sure whether you could say that's a bad thing or a good thing. Okay, so what's my style here for how many things am I going to try and test in the same function? I don't know. I think it would be more efficient to actually just put all of the possibilities in this one expectation, this one IT, which is an expectation. Even though if something goes wrong, it will be harder to debug. So that's a matter of taste, but let's try it. So, all right, what I need to kind of like have some sort of test data, if you like, that I can work on. So what I'm going to do is I'm going to say const e1 equals geometric e1. Okay, that means I've got a local e1 that I don't need to continually write geometric.e1, geometric, dot all the time. Similarly for e2. E2, okay. And now I'm thinking, it would be kind of handy if I had like a sort of a geometric that could a constant that could represent both one, scalar one, and also could another one that can represent e1 wedge e2. So I kind of want something like this. Const 1 equals new geometric 1, 0, 0, 0. Okay, that's 1. And I want another one that is going to represent like e1 wedge e2. Well, creating a name for this, okay, I'll tell you what it is on the right hand side first. I want it to be this. Okay, creating a name for this is kind of a little awkward, right? I mean, I could call it e1 e2 because e1 e2 is actually the same as e1 wedge e2. So, that'll be okay. But actually, I'm going to give it another name, and I'm going to call it capital I. Okay. So, capital I it's almost a convention. Capital I represents this highest grade element of the algebra, which in this case is E1 wedge E2. And the use of capital I is kind of suggestive. And I'm not going to say why it is right now, but some of you might kind of be able to guess. Okay, so we'll kind of come back to that. And you'll actually see it in the calculations. All right, so what I want to do is something like this. I want to kind of like multiply these things together. So I want to write like const result and equals, and I want to do something like e1.mul. So here I'm not being systematic yet. I'm just kind of like doing the example. So I want to do const result equals that, and then I want to say something like expect result dot a to b, and well, e1 wedge e2, e1 multiplied by e2 is just the same as e1 dot e2, which is 0, plus e1 wedge e2, which is the bivector. So the a should be 0. So I sort of want to do this, and I kind of want to do the same for all of the other parts. And you see that, oh my goodness, our testing is going to be kind of like becoming kind of crazy long, right? So it's almost like we need a helper function that can help us check that in fact E1 multiplied by E2 is actually, it's kind of the same as I. That's what it is, right? So I'd really like to say something like, do something like this, check equal, and I want to say E1 dot multiplied by E2. I want to check that that's equal to I. Right, and that would be like I could write the tests very easily if I had something like that, but I don't have the check equal function. So I'm going to create that function. So function check equal, and we're going to have a left-hand side, which is a geometric, and a right-hand side, which is a geometric. All right, and yeah, this is just going to call expect on each one of them. So we're going to just say expect that the left-hand side dot a to be dot to be right-hand side dot a. Okay, and if this fails, I could report left-hand side dot a equals $a, and the right-hand side dot a equals, oops, sorry, I'm kind of being silly here. That's left-hand side dot a equals LHS dot a, and this is right-hand side dot a. Okay. So if it fails, we should get to C. Okay, check equal here is working, and we need to do it for all components. So LHS.x, whoops, x, y, and b. Right-hand side, x, y, and b. Oops, x, y, and b. Sorry, this is a little tedious, but I assume that while I'm doing this tedious stuff, you're kind of like thinking about other questions and problems and stuff, so probably not a bad use of time. Okay, so now we've got something that I think is a little bit more convenient for us. We can go check equal, right? And let's just kind of like check that this is actually doing something. If we say check equal E1, and there we go. It doesn't tell us what we're actually doing, unfortunately. That would be kind of nice. I would say that probably what we could do is we could print out what the left-hand side is actually. So here's the actual problem, but then we could kind of like, no, this is good enough. This is good enough. I mean, recall that I did say before that this is an engineering trade-off. When we do this, if everything's working, then it's it's great. If it fails, then we're going to have to spend a little bit more time kind of like debugging and stuff. But I think that's going to be kind of rare, and so I think I'm just kind of like going to be more economical in my tests here. Okay, so let's sort of systematically then build up our tests. So I'm going to be systematic. So I'm going to do one, and I'm going to just do this in a kind of like a sort of an order, and a kind of like build up, what we'd call a sort of a Cartesian product. So 1 times 1, I expect that to be 1, right? And I'm not even going to look at my table anymore, right? I'm actually just going to sort of do this in my head and check it works. 1 times E1. That should be the same as E1. Yeah, looks good. And obviously I can do the other two. 1 times E2 should be E2, good. And 1 times I should be I. Okay. Let's just pause 1 second just to consider something. Now you may be wondering, like, David, you're not actually including like the scalar factors in here. You just got like 1, 1e1, 1e2, and 1i. Isn't it possible then that these tests may not be detecting, you might have hard coded or something a value to be 1 internally in geometric, and so the test passed, but in fact you've hard coded it. Well, I'm kind of going to go from a sort of a reasonableness kind of argument here and say, I guarantee you that this is kind of like pretty much testing it probably, efficiently, because it would be rather inconceivable for me to hard code and actually get the right results just by putting, hard coding 1. But if you feel like you want to write other tests that check that it's scaling correctly, then you can do that. I think this, on the other hand, this I think is going to kind of cover it. All right, so let's proceed. So we've done 1 times everything. If I just copy this for expedience sake, and I'm going to put a little break in there, and I'm going to start changing the leading value to E1, and I want to get all of these working. So let's try E1. E1 times 1 should just be E1. Good. E1 times E1 should just be 1. Okay, so I'm going to put a 1 in there. E1 times E2 will be E1 wedge E2, which is I. Okay, and E1 times I is E1 times E1 E2, which is just E2. Okay, so we're halfway there. And the next one, E2 multiplied by 1 should be E2. E2 multiplied by E1, this is interesting. E2 times E1 is just E2 E1, which is minus E1 E2, which is minus I. So we actually do have a neg, if I recall. Yeah. So I can take I can negate it. As long as I trust my neg, now we should really, have tests for neg now, automated testing for neg, but we'll do that. But looks good, right? So we'll carry on. Let's do E2 times E2, that's 1. And I'm just kind of, every time I do this, I'm kind of keeping my eye on the testing over here. It's like I see it go red and I go, good, I've got a failing test. Now I'm, I know that I'm actually fixing it. E2 times I is E2 times E1 E2. And I'm mentally kind of flipping the I, so it's E2 E1, but that's going to be a minus sign, so I'm going to get a minus E1. So this should be E1 dot neg. And we're passing, okay? And now we're on the last one. Copy that. Here's I. Oh, I don't want to do them all at one go. So Control Z. If I do them all in one go, I can't see it being fixed. I times 1 is just I. Yes. I times E1. So that's E1, E2 times E1. So I need to reverse. I need to do a reverse, which introduces a minus sign. Then the E1s will cancel. So I'm going to get an E2 neg, right? Yay, good. Okay. I times E2, that's E1, E2 times E2. The E2s are going to sort of become E2.E2 and then 1. So this should be just E1. Good. And then I times I. Ooh, got to think a little bit more for this one. Okay, I times I, that's E1 wedge E2 times E1 wedge E2, but E1 wedge E2 is just E1 E2. So we've got E1 E2 times E1 E2. And you can see now how the geometric product is starting to help us, because it enables us to actually, using that associative rule, we can now multiply sort of, directly, but we still need to do a flip to get the things in the right order. So we're going to we're going to flip one side of this. It doesn't matter which one. So that's going to introduce a minus sign, and then we're going to get e2 times e2, and then an e1 times e1, and those both are going to give us 1. So the final result is that it's minus 1. So I want 1 neg, and it works. Cool. So that's it. So a couple of things I would say here, just kind of like draw your attention to. One is that you can count here that we've got 16 multiplications arising from just a single geometric number multiplication. And I mentioned before that this is there's a general theme that as you use numbers that are more structured, they become more powerful and more expressive. So an example of that is a complex number contains 2 parts, and that is much more powerful in some way than just a simple, what we call them real numbers, but a single number. Our geometric algebra number here, the one so far, what we've got here, this geometric number of the plane, contains 4 numbers. And it has a lot more multiplications than a complex number. In fact, if you think about it, the reason why we have 16 is because 4 times 4 is 16. And the reason why we have 4 is because it's basically 2 raised to the power of the number of dimensions. There are 2 dimensions, so it's 2 squared. So you can see that as we go up in dimensions, like as we go to 3 dimensions, we are going to get a lot more multiplications. So it's just, it's kind of wild how powerful this stuff becomes. And if you kind of like carry on with geometric algebra, you're going to realize that we go from what I would call here a very sort of literal vector kind of geometric algebra, where our vectors kind of represent points. You could go to like projective algebras, where you embed your plane inside 3D space, and that extra dimension gives you more expressive power. You can express ideas that you couldn't do with just 2 dimensions. And we can kind of like go on with space-time, adding time dimensions, and time dimensions are hyperbolic as well. And so in addition to going up in dimensions, you start also to get very kind of counterintuitive behavior. It's not Euclidean anymore. So pretty exciting stuff. Okay, so we're just kind of like on the road to that. Okay, so the second thing I would like to just kind of like draw your attention to is I times I. Okay, I times I is minus 1. And that should remind you of complex numbers. And so, I think there's a couple of things to be mentioned here. Whenever people think of, the square root of minus 1, they might think of, some symbol I, and they just think of complex numbers. But in fact, you're going to see in geometric algebra that there are many things that square to the minus 1. So geometric algebra is going to open up a whole bunch of new ways of actually visualizing situations where you have the square root of minus 1. And this is going to really help in rotations and so forth. Okay, so I have showed you here how to do multiplication. I think we're going to wrap it up here. So thanks for staying with the course so far. If you got this far, then this is where the fruits kind of like really start to happen. I think we are probably at about episode number 9 or so right now, and the videos have probably been averaging somewhere around about 45 minutes. We're not at 10 hours, maybe we're about like 6 or 7 hours. It's a pretty good investment actually, in terms of what you're going to be able to do, even just with this geometric number. So I'm going to leave it perhaps as an exercise for you to take a look at the exterior product. So I'm just going to hide this, not hide the documentation. I want to stop it executing. Our exterior product in our geometric number is not complete because we didn't think at the time about how to extend it to A, wedge B, wedge C, three vectors wedged together. And what we want to do is we want to make sure that our exterior product contains everything that we need. Okay, in other words, we can multiply everything by everything. Okay, so I'm going to leave that as an exercise for you. I will probably do that as a separate video. The next video, I'm just going to run through that. But if you can implement that and you get it working and you put automated tests on it, oh, and by the way, you'll need a 0, right? Because many things are going to come out to 0. So obviously you can kind of create another constant in here called 0. And you might even want to enhance your geometric so that I is sort of similar to the way that E2 works. It's a constant that's just available in the geometric. Because it'll just be a very convenient kind of constant just to grab. And in fact, we'll be able to use it to do a little bit of optimization if we get a little bit kind of like clever later on. Okay, that just about does it. I hope you enjoyed this video. I know that it must seem like, wow, this is just a crazy amount of work, but just think how powerful this mathematical object is going to be. And we will show that in upcoming applications of this geometric number that you have created. Okay, take care. Happy coding. See you next time. If you like this video, please hit the like button. It really helps me because I know that people are watching it, and then it helps me, motivates me to write more videos. And if you really like it, subscribe to the video to hear more of these about what's kind of coming along. Take care. Bye-bye.